Alright, last exercise. This is again a bit long, this problem set. Please also comment below how these problem sets are for you. Too difficult, too long, too easy, too short. I don't think they are too short. Maybe I should always give 2 weeks time and upload new lessons every 2 weeks. I'm not sure. Please leave a comment. So we have these two permutations in S4, and now we conjugate this here with pi. Or this here is the conjugate of sigma with pi. Conjugation is a very important operation on a group. We don't know yet why, but we will see that in some weeks. So we build pi sigma pi inverse. I stop writing these circles here for composition. So this is pi, this is sigma. Now remember, the inverse of a cycle is simply the cycle written backwards. Usually I would have to start with a 2 here in front, but that's okay. Now let's see what this here does to the number 1. I plug in 1 from the right side, nothing happens. 1 goes to 4, 4 goes to 3, so 1 goes to 3. Next we plug in the 3, 3 goes to 4, 4 goes to 2, 2 goes to 4. So 3 ends up going to number 4. Okay, and now the last thing we plug in is the 4. 4 is moved to 2, 2 goes to 3, 3 goes to 2, so we again end up with a 4 cycle. This is important. And even more important, the question was, what do these numbers have to do with pi? Well, 1 is pi of 1 because pi doesn't move the 1. So I could have written it like that. Now what is 3? 3 is actually pi applied to 4 because pi moves 4 to 3. So instead of the 4 here, I end up with pi of 4. Same here, 4 is the image of 2 under pi, so this 2 gets replaced by pi of 2, and finally this 2 here is the image of 3 under pi because pi moves 3 to 2. So there seems to be a very simple formula for obtaining the conjugate of a cycle. Simply take the permutation you're conjugating with and replace all these entries here by the image of them under pi. And this will be our general claim that we try to prove. Okay, now the claim is simple enough to write down. So let sigma be actually any permutation in Sn. We know that we can decompose sigma into disjoint cycles. So it actually suffices to prove this for one cycle, because if I know it for one cycle, I know it for a composition of any number of disjoint cycles. So A1 to AM is the first cycle. I could write here AM1 and then AM2, but this just blows up the notation. So this means sigma is a composition of disjoint cycles. Then the claim is, if I take any permutation in Sn and conjugate sigma with it, the cycle structure remains the same. Hence the headline of this exercise, conjugating does not change the cycle structure. And the cycles of the conjugate are very easily obtained by simply plugging in these entries here into pi. That's it. And then of course the same here, pi of B1 and so on. All right, let's try to prove this. And again, I think this will be easy to follow, or not too hard to follow, but to write down on your own, for a beginner, I think it's pretty hard. So at the end of the day, we want to show that this permutation, this clearly is another permutation, is the same as this permutation. So I call this one rho, and here the right-hand side I abbreviate by tau. And we have to show that rho is equal to tau. How do we do that? We show that they have the same effect on all the numbers from 1 to n. And we start as follows. We assume that the natural numbers I and j between 1 and n are neighbors in one of the cycles of sigma, meaning that, for example, here is the number 3 and here is the number 6 adjacent to each other, so they are neighbors. Or we shouldn't forget this case, if I is the last entry, then I also call this one a neighbor because I gets mapped to j. But we know that we can rearrange or permutate all those cycles cyclically, so I always can avoid this case by rearranging the cycle, so we will not worry about that anymore. But we haven't forgotten a case. So, by definition, this means j is sigma of I. Okay, now comes a tricky part. We do not plug in j or sigma of I into rho, but we use pi of I. Why? Because here we have pi inverse. So if we spell that out, this is pi sigma pi inverse pi of I. By associativity, I do not have to worry about parentheses. So here, these two cancel because they are the identity. So I end up with pi of sigma of I. All right? Pi of sigma of I. But now, by definition, sigma of I is j. So this is pi of j. So, but what does that mean? That means exactly that if these two are neighbors in the cycle decomposition of sigma, then pi of I is a neighbor of pi of j. And this is exactly what tau does, because here tau moves pi of I, one entry here, to the next one pi of j. If I and j, so if I and j were neighbors here in this cycle decomposition of sigma, then pi of I and pi of j are neighbors in the cycle decomposition here, and this exactly proves what we wanted to show, namely rho is equal to tau, hence the claim follows. Now wait a minute, you might say, did we really check all the numbers? We simply took neighbors here. Well, first of all, pi is a bijective map from the numbers 1 to n to the numbers 1 to n. So clearly here I get all the numbers, but they do not need to be neighbors because I could also have a one cycle in this decomposition. Then there are no neighbors. But that doesn't matter because then if here this does not occur in one of the longer cycles, a length greater than 1, it simply stays fixed by both permutations. Okay, sorry, that was not perfectly clear, so let's try to clean this up. So now first of all, I could have written here ak and ak plus 1, so it would have been clearer that they are neighbors. And though here I would have had am and a1, which again can be avoided by cyclic permutation. But this blows up the notation unnecessarily, I think. So this should be clear enough with I and j instead of that. But I should have said in the end, by definition, tau, if ij is in the cycle decomposition of sigma, then by definition here in tau we have pi of I and pi of j as neighbors. So this is this equality sign here, because by definition tau moves pi of I to pi of j. So now for the case, what if this is in a one cycle, the I? We always assume that here we have at least two elements in a cycle, otherwise I can't have neighbors. So you could argue that, well, we have forgotten this case. No, not really, because let's assume we have a one cycle in the decomposition of sigma, for example, I, or I could call it A, whatever. This means that sigma of I is I by definition. A one cycle doesn't move this number here, so that's why we leave it out normally. So then I claim that pi of I is fixed by rho and by tau. Why? First of all, if I plug in pi of I into rho by the same argument as here, I end up with pi of sigma of I, like that. But sigma of I is I, so rho of this simply leaves pi of I where it is. So the left-hand side leaves pi of I fixed. The right-hand side, by definition, if here we have a one cycle in sigma, then tau is defined as containing the one cycle pi of I. Now if I plug in pi of I into this one cycle here, obviously it does not get moved as well. So I have tau of pi of I is pi of I, and now we are really done. As a word of caution, if you stop here and think, well, it's somehow clear, and if you can't clearly explain it to someone else, then you haven't understood it completely. So always make sure that there are no questions open. Even if you don't write them down in detail, you could say, well, if it doesn't get moved pi of I, then it doesn't get moved by both sides. But you should be aware if you have understood it completely or not. All right, that's it. Sorry again for the length, but I think there were some nice exercises here. And maybe next week we try to tune it down a bit in the next problem set. All right, see you then. Bye-bye.